Hey everyone, Brian Lee here from Fools and Sages with part 3 of Henri Bergson's Creative Evolution. Uh, got the fire going, got the beverage, so get yourself comfortable and we'll get into part 3. Now, this is my part 3. Within his book, we're still in chapter 1. In chapter 1, just to catch us up again, is called The Evolution of Life Mechanism and Teleology. And these are two sorts of explanations for change in creatures. And we read in the first part of duration in general, unorganized bodies, and abstract time, and then organized bodies and real duration. Time is a thing for Bergson. And then individuality in the process of growing old. Again, time. Then the next section, which we were just finishing last time, is of transformism and the different ways of interpreting it. That is, that animals change over time. And how do we interpret it? Radical mechanism and real duration, which is kind of the Darwinian, it's just mechanistic. The relation of biology to physics and chemistry. And then radical finalism. Finalism is another word for teleology. Telos in Greek, I mentioned before, means an end. And so the idea that all this changing and developing is moving towards an end is one of the directions of explanation, and a very intense flavor of it is radical finalism, which is what he's referring to here. So radical finalism and real duration, the relation of biology to philosophy. And then the section we're getting into today is called The Quest of a Criterion, examination of the various theories with regard to a particular example. Darwin and insensible variation, De Vries and sudden variation, Eimer and orthogenesis, neo-Lamarckism and the hereditability of acquired characters. So those are the different theories regarding a particular example. And then the final part of chapter 1 is the result of that inquiry, of that quest, which is going to be the vital impulse, his idea of élan vital. So we finished the last section with a little paragraph he's got in italics here. And it says, pure mechanism then would be refutable from the argument he just made and he left us with last time, and finality, in the special sense in which we understand it, would be demonstrable in a certain aspect if it could be proved that life may manufacture the like apparatus by unlike means on divergent lines of evolution, and the strength of the proof would be proportional to both the divergence between those lines of evolution thus chosen and to the complexity of the similar structures found in them. So basically what he's saying is that if nature tries to do the same thing two different ways in two different places, it implies that those both are trying to get to the same end, or telos. So that's a kind of an argument for this, what did he call it? A special sense in which he understands the idea of finality or a goal. So going on to his text after that paragraph in italics, we're starting on page 55. It'll be said that resemblance of structure is due to sameness of the general conditions in which life has evolved, that these permanent outer conditions may have imposed the same direction on the forces constructing this or that apparatus, in spite of the diversity of transient outer influences and accidental interchanges. We are not, of course, blind to the role which the concept of adaptation plays in the science of today. Biologists certainly do not all make the same use of it. Some think the outer conditions capable of causing change in organisms in a direct manner, in a definite direction, through physicochemical alterations induced by them in the living substance, such as the hypothesis of Eimer, for example. Others, more faithful to the spirit of Darwinism, believe the influence of conditions works indirectly only, through favoring in the struggle for life those representatives of a species which the chance of birth has best adapted to the environment. In other words, some attribute a positive influence to outer conditions and say that they actually give rise to variations, while others say these conditions only have a negative influence and merely eliminate variations, that is, the weakest. But in both cases, the outer conditions are supposed to bring about a precise adjustment of the organism to its circumstances. Both parties then will attempt to explain mechanically, By adaptation to similar conditions, the similarities of structure, which we think are the strongest argument against mechanism. So we must at once indicate in a general way before passing to the detail why explanations from adaptation seem to us insufficient. Let us first remark that of the two hypotheses just described, the latter is the only one which is not equivocal. The Darwinian idea of adaptation by automatic elimination of the unadapted is a simple and clear idea. But just because it attributes to the outer cause which controls evolution a merely negative influence, it has great difficulty in accounting for the progressive and, so to say, rectilinear development of complex apparatuses such as we're about to examine. How much greater will this difficulty be in the case of the similar structure of two extremely complex organs on two entirely different lines of evolution? An accidental variation, however minute, implies the working of a great number of small physical and chemical causes. An accumulation of accidental variations, such as would be necessary to produce a complex structure, requires therefore the concurrence of an almost infinite number of infinitesimal causes. Why should these causes, entirely accidental, recur the same and in the same order at different points of space and time? No one will hold that this is the case, and the Darwinian himself will probably merely maintain that identical effects may arise from different causes, that more than one road leads to the same spot. But let us not be fooled by a metaphor. The place reached does not give the form of the road that leads there. While an inorganic structure is just the accumulation of those small differences which evolution has had to go through in order to achieve it, the struggle for life and natural selection can be of no use to us in solving this part of the problem, for we're not concerned here with what has perished. We have only to do with what has survived. Now, we see that identical structures have been formed on independent lines of evolution by a gradual accumulation of effects. How can accidental causes occurring in an accidental order be supposed to have repeatedly come to the same result? The causes being infinitely numerous and the effect infinitely complicated. The principle of mechanism is that, quote, the same causes produce the same effects, unquote. This principle, of course, does not always imply that the same effects must have the same causes, but it does involve this consequence in the particular case in which the causes remain visible in the effect that they produce and are indeed its constitutive elements. That two walkers, starting from different points and wandering at random, should finally meet is no great wonder. But that throughout their walk they should describe two identical curves exactly superimposable on each other is altogether unlikely. The improbability will be the greater, the more complicated the routes, and it will become impossibility if the zigzags are infinitely complicated. Now, what is this complexity of zigzags as compared to that of an organ in which thousands of different cells, each being itself a kind of organism, are arranged in a definite order? Let us turn then to the other hypothesis and see how it would solve the problem. Adaptation, it says, is not merely elimination of the unadapted. It's due to the positive influence of outer conditions that have molded the organism on their own form. This time, similarity of effects will be explained by similarity of cause. We shall remain apparently in pure mechanism. But if we look closely, we shall see that the explanation is merely verbal, and that we are again the dupes of words, and that the trick of the solution consists in taking the term adaptation in two entirely different senses at the same time. If I pour into the same glass by turns water and wine, the two liquids will take the same form, and the sameness in form will be due to the sameness in adaptation of content to container. Adaptation here really means mechanical adjustment. The reason is that the form to which the matter has adapted itself was there, ready-made, and has forced its own shape onto the matter. But in the adaptation of an organism to the circumstances it has to live in, where is the pre-existing form awaiting its matter? The circumstances are not a mold into which life is inserted and whose form life adopts. This is indeed to be fooled by a metaphor. There is no form yet, and the life must create a form for itself, suited to the circumstances which are made for it. It will have to make the best of these circumstances, neutralize their inconveniences, and utilize their advantages. In short, respond to outer actions by building up a machine which has no resemblance to them. Such adapting is not repeating, but replying, an entirely different thing. If there is still adaptation, it will be in the sense in which one may say of the solution of a problem of geometry, for example, that it is adapted to the conditions. I grant, indeed, that adaptation, so understood, explains why different evolutionary processes result in similar forms. The same problem, of course, calls for the same solution, but it is necessary then to introduce, as for the solution of a problem of geometry, an intelligent activity, or at least a cause which behaves in the same way. This is to bring in finality again, and a finality this time more than ever charged with an anthropomorphic elements. In a word, if the adaptation is passive, if it is a mere repetition in the relief of what the conditions give in the mold, it'll build up nothing that one tries to make it build. And if it is active, capable of responding by a calculated solution of the problem which is set out in the conditions, that is going further than we do, too far indeed, in our opinion, in the direction we indicated in the beginning. But the truth is that there is a surreptitious passing from one of these two meanings to the other, a flight for refuge to the first whenever one is about to be caught in flagrante delicto of finalism by employing the second. It is really the second which serves the usual practice of science, but it is the first that generally provides its philosophy. In any particular case, one talks as if the process of adaptation were an effort of the organism to build up a machine capable of turning external circumstances to the best possible account. Then one speaks of adaptation in general, as if it were the very impress of circumstances passively received by an indifferent matter. But let us come to the examples. It would be interesting first to institute here a general comparison between plants and animals. One cannot fail to be struck with the parallel progress which has been accomplished on both sides in the direction of sexuality. Not only is fecundation itself the same in higher plants and in animals, since it consists in both in the union of two nuclei that differ in their properties and structure before their union and immediately after become equivalent to each other, but the preparation of sexual elements goes on in both under like conditions. It consists essentially in the reduction of the number of chromosomes and the rejection of a certain quantity of chromatic substance. And he quotes Guérin, Les connaissances actuelles sur la fécondation chez les phanerogames, in Paris, 1904. I probably slaughtered that. Yet vegetables and animals have evolved on independent lines, favored by unlike circumstances, opposed by unlike obstacles. Here are two great series which have gone on diverging. On either line, thousands and thousands of causes have combined to determine the morphological and functional evolution. Yet these infinitely complicated causes have been consummated in each series in the same effect. And this effect could hardly be called a phenomenon of adaptation. Where is the adaptation? Where is the pressure of external circumstance? There is no striking utility in sexual generation. It has been interpreted in the most diverse ways, and some very acute inquirers even regard the sexuality of the plant, at least, as a luxury which nature might have dispensed with. That's Mobius in Betrage sur l'Air von der Fortpflanzung der Gewächse in 1897. If you want to look that up. But we do not wish to dwell on facts so disputed. The ambiguity of the term adaptation and the necessity of transcending both the point of view of mechanical causality and that of anthropomorphic finality will stand out more clearly with simpler examples. At all times, the doctrine of finality has laid much stress on the marvelous structure of the sense organs in order to liken the work of nature to that of an intelligent workman. Now, since these organs are found on a rudimentary state in the lower animals, and since nature offers us many intermediaries between pigment spot of the simplest organisms and the infinitely complex eye of the vertebrates, it may just as well be alleged that the result has been brought about by natural selection perfecting the organ automatically. In short, if there is a case in which it seems justifiable to invoke adaptation, it is this particular one. For there may be discussion about the function and the meaning of such a thing as sexual generation, insofar as it is related to the conditions in which it occurs. But the relation of the eye to light is obvious. And when we call this relation an adaptation, we must know what we mean. If then we can show in this privileged case the insufficiency of the principles invoked on both sides, our demonstration will at once have reached a high degree of generality. Let us consider, for example, on which the advocates of finality have always insisted, the structure of such an organ as the human eye. They have had no difficulty in showing that in this extremely complicated apparatus, all the elements are marvelously coordinated. In order that vision shall operate, says the author of a well-known book on final causes, quote, the sclerotic membrane must become transparent in one point of its surface so as to enable luminous rays to pierce it. The cornea must correspond exactly with the opening of the socket. Behind this transparent opening, there must be refracting media. There must be a retina at the extremity of the dark chamber. Perpendicular to the retina, there must be an innumerable quantity of transparent cones permitting only the light directed in the line of their axes to reach the nervous membrane, etc., etc. And he's quoting Paul Genet here, The Final Causes, 1876. In reply, the advocate of final causes has been invited to assume the evolutionist hypothesis. Everything is marvelous indeed if one considers an eye like ours in which thousands of elements are coordinated in a single function. But take the function at its origin in the infusorian, like a worm, where it is reduced to the mere impressionability, almost purely chemical, of a pigment spot to light. This function, possibly only an accidental fact in the beginning, may have brought about the slight complication of the organ, which again induced an improvement of the function. It may have done this either directly through some unknown mechanism or indirectly, merely through the effect of the advantages it brought to the living being and the hold it thus offered to natural selection. Thus, the progressive formation of an eye as well contrived as ours would be explained by an almost infinite number of actions and reactions between the function and the organ without the intervention of other than mechanical causes. The question is hard to decide indeed when put directly between the function and the organ, as is done in the doctrine of finality, as also mechanism itself does. For organ and function are terms of different nature, and each conditions the other so closely that it is impossible to say a priori whether in expressing their relation we should begin with the first, as does mechanism, or with the second, as finalism requires. But the discussion would take an entirely different turn, we think, if we began by comparing together two terms of the same nature, an organ with an organ instead of an organ with its function. In this case, it would be possible to proceed little by little to a solution more and more plausible, and there would be the more chance of a successful issue the more resolutely we assume the evolutionist hypothesis. Let us place side by side the eye of a vertebrate and that of a mollusk, such as the common pecten. We find the same essential parts in each, composed of analogous elements. The eye of the pecten presents a retina, a cornea, a lens of circular structure like our own, cellular structure like our own, rather. There's even that peculiar inversion of retinal elements which is not met with in general in the retina of the invertebrates. Now, the origin of mollusks may be a debated question, but whatever opinion we hold, all are agreed that mollusks and vertebrates separated from their common parent stem long before the appearance of an eye so complex as that of the pecten. Whence then the structural analogy, which is to say, from where? Let us question on this point the two opposed systems of evolutionist explanation in turn, the hypothesis of purely accidental variations and that of the variation directed in a definite way under the influence of external conditions. The first, as is well known, is presented today in two quite different forms. Darwin spoke of very slight variations being accumulated by natural selection. He was not ignorant of the facts of sudden variation, but he thought these sports, as he called them, were only monstrosities incapable of perpetuating themselves, and he accounted for the genesis of species by an accumulation of insensible variations, insensible in italics. Such is still the opinion of many naturalists. It is tending, however, to give way to the opposite idea that a new species comes into being at all at once by the simultaneous appearance of several new characters, all somewhat different from the previous ones. This latter hypothesis, already proposed by various authors, notably by Bateson in a remarkable book called Materials of the Study of Variation, published in London in 1894, especially page 566, has become deeply significant and acquired great force since the striking experiments of Hugo de Vries. This botanist, working on Oenothera lamarckiana obtained at the end of a few generations a certain number of new species. The theory he deduced from his experiments is of the highest interest. Species pass through alternate periods of stability and transformation. When the period of mutability occurs, unexpected forms spring forth in a great number of different directions. And there he's quoting De Vries, Die Mutation Theory from Leipzig, 1901. We will not attempt to take sides between this hypothesis and that of insensible variations. Indeed, perhaps both are partly true. We wish merely to point out that if the variations invoked are accidental, they do not, whether great or small, account for a similarity of structure such as we have cited. Let us assume to begin with the Darwinian theory of insensible variations and suppose the occurrence of small differences due to chance and continually accumulating. It must not be forgotten that all the parts of an organism are necessarily coordinated. Whether the function be the effect of the organ or its cause, it matters little. One point is certain: the organ will be of no use and will not give selection a foothold unless it functions. However, the minute structure of the retina may develop, and however complicated it may become, such progress, instead of favoring vision, will probably hinder it if the visual centers do not develop at the same time, as well as several parts of the visual organ itself. If the variations are accidental, how can they ever agree to arise in every part of the organ at the same time, in such way that the organ will continue to perform its function? Darwin quite understood this. It's one of the reasons why he regarded variation as insensible. The Origin of Species, Chapter 6. For a difference which arises accidentally at one point of the visual apparatus, if it be very slight, will not hinder the functioning of the organ, and hence the first accidental variation can, in a sense, wait for complementary variations to accumulate and raise vision to a higher degree of perfection. Granted, but while the insensible variation does not hinder the functioning of the eye, neither does it help it, so long as the variations that are complementary do not occur. How, in that case, can the variation be retained by natural selection? Unwittingly, one will reason as if the slight variation were a toothing stone set upon by the organism and reserved for a later construction. This hypothesis, so little comfortable to the Darwinian principle, is difficult enough to avoid even in the case of an organ which has been developed along one single main line of evolution, i.e. the vertebrate eye. But it is absolutely forced upon us when we observe the likeness of structure of the vertebrate eye and that of the mollusks. How could the same small variations, incalculable in number, have ever occurred in the same order on two independent lines of evolution if they were purely accidental? And how could they have been preserved by selection and accumulated in both cases the same in the same order when each of them taken separately was of no use? Let us turn then to the hypothesis of sudden variations and see whether it'll solve the problem. It certainly lessens the difficulty on one point, but it makes it much worse on another. If the eye of the mollusk and that of the vertebrae have both been raised to their present form by a relatively small number of sudden leaps, I have less difficulty in understanding the resemblance of the two organs than if this resemblance were due to an incalculable number of infinitesimal resemblances acquired successively. In both cases, it is chance that it operates, but in the second case, chance is not required to work the miracle it would have to perform in the first. Not only is the number of resemblances to be added somewhat reduced, but I can also understand better how each could be preserved and added to the others, for the elementary variation is now considerable enough to be an advantage to the living being, and so to lend itself to the play of selection. But here there arises another problem no less formidable, vis-a-vis, how do all the parts of the visual apparatus suddenly change, remain so well coordinated that the eye continues to exercise its function? For the change of one part alone will make vision impossible unless this change is absolutely infinitesimal. The parts must then all change at once, each consulting the others. I agree that a great number of uncoordinated variations may indeed have arisen in less fortunate individuals, that natural selection may have eliminated these, and that only the combination fit to endure, capable of preserving and improving vision, has survived. Still, this combination had to be produced. And supposing chance to have granted this favor once, can we admit that it repeats the self-same favor in the course of the history of a species, so as to give rise every time all at once to new complications marvelously regulated with reference to each other, and so related to former complications as to go further on in the same direction? How especially can we suppose that by a series of mere accidents these sudden variations occur, the same in the same order, involving in each case a perfect harmony of elements more and more numerous and complex along two independent lines of evolution? The law of correlation will be invoked, of course. Darwin himself appealed to it, Chapter 1, Origin of Species. It'll be alleged that a change is not localized in a single point in the organism, but it has its necessary recoil on other points. The examples cited by Darwin remain classic. White cats with blue eyes are generally deaf. Hairless dogs have imperfect dentition, etc. Granted. But let us not play now on the word correlation. A collective whole of solidary changes is one thing. A system of complementary changes, changes so coordinated as to keep up and even improve the functioning of an organ under more complicated conditions, is another. That an anomaly of the pilus system should be accompanied by an anomaly of dentition is quite conceivable without our having to call for a special principle of explanation. For hair and teeth are similar formations, and the same chemical change of the germ that hinders the formation of hair would probably obstruct that of teeth. It may be for the same sort of reason that white cats with blue eyes are deaf. In these different examples, the correlative changes are only solidary changes, not to mention the fact that they're really lesions, namely diminutions or suppressions, and not additions, which makes a great difference. But when we speak of correlative changes occurring suddenly in the different parts of the eye, we use the word in an entirely new sense. This time there is a whole set of changes, not only simultaneously, not only bound together by community of origin, but so coordinated that the organ keeps on performing the same simple function and even performs it better. That a change in the germ which influences the formation of the retina may affect at the same time also the formation of the cornea, the iris, the lens, the visual centers, etc. I admit, if necessary, although they are formations that differ much more from one another in their original nature than do probably hair and teeth. But that all these simultaneous changes should occur in such a way as to improve or even merely maintain vision, this is what, in the hypothesis of sudden variation, I cannot admit, unless a mysterious principle is to come in, whose duty it is to watch over the interests of the function. But this would be to give up the idea of accidental variation. In reality, these two senses of the word correlation are often interchanged in the mind of the biologist, just like the two senses of the word adaptation. And the confusion is almost legitimate in botany, that science in which the theory of the formation of species by sudden variation rests on the firmest experimental basis. In vegetables, function is far less narrowly bound to form than in animals. Even profound morphological differences, such as a change in the form of leaves, have no appreciable influence on the exercise of function, and so do not require a whole system of complementary changes for the plant to remain fit to survive. But it is not so in the animal, especially in the case of an organ like the eye, a very complex structure and very delicate function. Here it's impossible to identify changes that are simply solidary with changes which are also complementary. The two senses of the word correlation must be carefully distinguished. It would be a downright paralogism to adopt one of them in the premise of the reasoning and the other in the conclusion. And this is just what is done when the principle of correlation is invoked in explanation of detail in order to account for complementary variations, and then correlation in general is spoken of as if it were any group of variations provoked by any variation of the germ. Thus, the notion of correlation is first used in current science as it might be used by an advocate of finality. It's understood that this is only a convenient way of expressing oneself, that one will correct it and fall back on pure mechanism when explaining the nature of the principles and the turning from science to philosophy. And one does then come back to pure mechanism, but only then by giving a new meaning to the word correlation, a meaning which would now make correlation inapplicable to the detail it is called upon to explain. To sum up, if the accidental variations that bring about evolution are insensible variations, some good genius must be appealed to, the genius of the future species, in order to preserve and accumulate these variations, for selection will not look after this. If, on the other hand, the accidental variations are sudden, then for the previous function to go on, or for a new function to take its place, all the changes that have happened together must be complementary. So we have to fall back on the good genius again, this time to obtain the convergence of simultaneous changes, as before to be assured of the continuity of direction of successive variations. But in neither case can parallel development of the same complex structures on independent lines of evolution be due to a mere accumulation of accidental variations. So we come to the second of the two great hypotheses we have to examine. Suppose the variations are due not to accidental and inner causes, but to the direct influence of outer circumstances. Let us see what line we should have to take on this hypothesis to account for the resemblance of eye structure in two series that are independent of each other from the phylogenetic point of view. Though mollusks and vertebrae have evolved separately, both have remained exposed to the influence of light. And light is a physical cause bringing forth certain definite effects. Acting in a continuous way, it has been able to produce a continuous variation in a constant direction. Of course, it is unlikely that the eye of the vertebrate and that of the mollusk have been built up by a series of variations due to simple chance. Admitting even that light enters into the case as an instrument of selection in order to allow only useful variations to persist, there is no possibility that the play of chance, even thus supervised from without, should bring about in both cases the same juxtaposition of elements coordinated in the same way. But it would be different, supposing that light acted differently on the organized matter so as to change its structure and somehow adapt the structure to its own form. The resemblance of the two effects would then be explained by the identity of the cause. The more and more complex eye would be something like the deeper and deeper imprint of light on a matter which, being organized, possesses a special aptitude for receiving it. But can an organic structure be likened to an imprint? We've already called attention to the ambiguity of the term adaptation. The gradual complication of a form which is being better and better adapted to the mold of outward circumstance is one thing. The increasingly complex structure of an instrument which derives more and more advantage from these circumstances is another. In the former case, the matter merely receives an imprint. In the second, it reacts positively. It solves a problem. Obviously, it's the second sense of the word adapt that is used when one says that the eye has become better and better adapted to the influence of light. But one passes more or less unconsciously from this sense to the other, and a purely mechanistic biology will strive to make the passive adaptation of an inert matter, which submits to the influence of its environment, mean the same as the active adaptation of an organism which derives from this influence an advantage it can appropriate. It must be owned, indeed, that nature herself appears to invite our mind to confuse these two kinds of adaptation, for she usually begins by a passive adaptation, where later on she will build up a mechanism for active response. Thus, in the case before us, it is unquestionable that the first rudiment of the eye is found in the pigment spot of the lower organisms. This spot may indeed have been produced physically by the mere action of light, and there are a great number of intermediaries between the simple spot of pigment and a complicated eye like that of the vertebrates. But from the fact that we pass from one thing to another by degrees, it does not follow that the two things are of the same nature. From the fact that an orator falls in at first with the passions of his audience in order to make himself master of them, it will not be concluded that to follow is the same as to lead. Now, living matter seems to have no other means of turning circumstances to good account than by adapting itself to them passively at the outset. Whereas it has to direct a movement, it begins by adopting it. Life proceeds by insinuation. The intermediate degrees between a pigment spot and an eye are nothing to the point. However numerous the degrees, there will still be the same interval between the pigment spot and the eye as between the photograph and the photographic apparatus. Certainly, the photograph has been gradually turned into a photographic apparatus. But could light alone, a physical force, ever have provoked this change and converted an impression left by it into a machine capable of using it? It may be claimed that considerations of utility are out of place here, that the eye is not made to see, but that we see because we have eyes, that the organ is what it is, and utility is a word by which we designate the functional effects of the structure. But when I say that the eye, quote, makes use of, unquote, light, I do not merely mean that the eye is capable of seeing. I allude to the very precise relations that exist between this organ and the apparatus of locomotion. The retina of vertebrae is prolonged in an optic nerve, which again is continued by cerebral centers connected with motor mechanisms. Our eye makes use of light in that it enables us to utilize by movements of reaction the objects that we see to be advantageous and to avoid those which we see to be injurious. Now, of course, as light may have produced a pigment spot by physical means, so it can physially determine the movements of certain organisms. Ciliated infusoria, for instance, react to light, but no one will hold that the influence of light has physically caused the formation of a nervous system, of a muscular system, of an osseous system, all things which are continuous with the apparatus of vision in vertebrate animals. The truth is, when one speaks of the gradual formation of the eye, and still more when one takes into account all that is inseparably connected with it, one brings in something entirely different from the direct action of light. One implicitly attributes to organized matter a certain capacity sui generis, the mysterious power of building up very complicated machines to utilize the simple excitation that it undergoes. Sui generis is like self-generation. But this is just what is claimed to be unnecessary. Physics and chemistry are said to give us the key to everything. Eimer's great work is instructive in this respect. It is well known what persevering effort this biologist has devoted to demonstrating that transformation is brought about by the influence of the external on the internal, continuously exerted in the same direction and not, as Darwin held, by accidental variations. His theory rests on observations of the highest interest, of which the starting point was the study of the course followed by the color variation of the skin of certain lizards. Before this, the already old experiments of Dorfmeister had shown that the same chrysalis, according as it was submitted to cold or heat, gave rise to very different butterflies, which had long been regarded as independent species, Vanessa levana and Vanessa prorsa. An intermediate temperature produces an intermediate form. We might class with these facts the important transformations observed in a little crustacean, Artemia salina, when the salt of the water it lives in is increased or diminished. In these various experiments, the external agent seems to act as a cause of transformation. But what does the word cause mean here? Without undertaking an exhaustive analysis of the idea of causality, we will merely remark that three very different meanings of this term are commonly confused. Cause may act by impelling, releasing, or unwinding. The billiard ball that strikes another determines its movement by impelling. The spark that explodes the powder acts by releasing. The gradual relaxing of the spring that makes the phonograph turn unwinds the melody inscribed on the cylinder. He's talking about phonographs that you used to crank and wind up like a watch, and then the spring would unwind, and that's what would turn the record. If the melody which is played to be the effect, and the relaxing of the spring the cause, we must say that the cause acts by unwinding. What distinguishes these three cases from each other is the greater or less solidarity between the cause and the effect. In the first, the quantity and quality of the effect vary with the quantity and quality of the cause. In the second, neither the quality nor the quantity of the effect varies with the quality and the quantity of the cause. The effect is invariable. In the third, the quantity of the effect depends on the quantity of the cause, but the cause does not influence the quality of the effect. The longer the cylinder turns by the action of the spring, the more of the melody I shall hear, but the nature of the melody or the part heard does not depend on the action of the spring. Only in the first case really does cause explain effect. In the others, the effect is more or less given in advance and the antecedent is invoked. The antecedent invoked is, in different degrees, of course, its occasion rather than its cause. Now, in saying that the saltiness of the water is the cause of the transformation of Artemia, or that the degree of temperature determines the color and marks of the wings of a certain chrysalis will assume on becoming a butterfly, is the word cause used in the first sense? Obviously not. Causality has here an intermediary sense between those of unwinding and releasing. Such indeed seems to be Eimer's own meaning when he speaks of the kaleidoscopic character of the variation, or when he says of the variation of organized matter works in a definite way, just as inorganic matter crystallizes in definite directions. And it may be granted, perhaps, that the process is a merely physical and chemical one in the case of the color changes of the skin. But if this sort of explanation is extended to the case of the gradual formation of the eye of the vertebrae, for instance, it must be supposed that the physical chemistry of living bodies is such that the influence of light has caused the organism to construct a progressive series of visual apparatus, all extremely complex, yet all capable of seeing and of seeing better and better. What more could be the most confirmed finalists say? What more could the most confirmed finalists say in order to mark out so exceptional a physiochemistry? And will not the position of a mechanistic philosophy become still more difficult when it's pointed out to it that the egg of a mollusk cannot have the same chemical composition as that of a vertebrae, that the organic substance which evolved towards the first of these two forms could not have been chemically identical with that of the substance which went in the other direction, and that nevertheless, under the influence of light, the same organ has been constructed in the one case as in the other. The more we reflect on it, the more we shall see that this production of the same effect by two different accumulations of an enormous number of small causes is contrary to the principles of mechanistic philosophy. We've concentrated the full force of our discussion upon an example drawn from phylogenesis, but ontogenesis would have furnished us with facts no less cogent. Every moment, right before our eyes, nature arrives at identical results in sometimes neighboring species by entirely different embryogenic processes. Observations of heteroblastia have multiplied in late years, and it's been necessary to reject the almost classical theory of the specificity of embryonic gills. Still keeping to our comparison between the eye of vertebrates and that of mollusks, we may point out that the retina of the vertebrae is produced by an expansion in the rudimentary brain of the young embryo. It's a regular nervous center which has moved toward the periphery. In the mollusk, on the contrary, the retina is derived from the ectoderm directly and not indirectly by means of the embryonic encephalon. Quite different, therefore, are the evolutionary processes which lead in man and in the pecten to the development of a like retina. But without going so far as to compare two organisms so distant from each other, we might reach the same conclusion simply by looking at certain various curious facts of regeneration in one and the same organism. If the crystalline lens of a triton be removed, it is regenerated by the iris. Now, the original lens was built out of the ectoderm, while the iris is of mesodermic origin. What is more, in the salamandra maculata, if the lens be removed and the iris left, the regeneration of the lens takes place at the upper part of the iris. But if this upper part of the iris itself be taken away, the regeneration takes place in the inner or retinal layer of the remaining region. You got to wonder who does all that. Thus, parts differently situated, differently constituted, meant normally for different functions, are capable of performing the same duties and even of manufacturing, when necessary, the same pieces of the machine. Here we have indeed the same effect obtained by different combinations of causes. Whether we will or no, we must appeal to some inner directing principle in order to account for this convergence of effects. Such convergence does not appear possible in the Darwinian, and especially the neo-Darwinian theory of insensible accidental variations, nor in the hypothesis of sudden accidental variations, or even in the theory that assigns definite directions to the evolution of the various organs by a kind of mechanical composition of the external with the internal forces. So we come to the only one of the present forms of evolution which remains for us to mention vis-a-vis neo-Lamarckism. It's well known that Lamarck attributed to the living being the power of trying by use or disuse of its organs, the power of varying. Let me just try that again. It's well known that Lamarck attributed to the living being the power of varying by use or disuse of its organs, and also of passing on the variation so acquired to its descendants. A certain number of biologists hold a doctrine of this kind today, which is to say 115 years ago. The variation that results in a new species is not, they believe, merely an accidental variation inherent in the germ itself, nor is it governed by a determinism sui generis, which develops definite characters in a definite direction, apart from every consideration of utility. It springs from the very effort of the living being to adapt itself to the circumstances of its existence. The effort may indeed be only the mechanical exercise of certain organs, mechanically elicited by the pressure of external circumstances, but it may also imply consciousness and will, and it is in this sense that it appears to be understood by one of the most eminent representatives of the doctrine, the American naturalist Cope, who wrote a book in 1887 called The Origin of the Fittest. Neo-Lamarckism is therefore, of all the later forms of evolutionism, the only one capable of admitting an internal and psychological principle of development, although it is not bound to do so. And it is also the only evolutionism that seems to us to account for the building up of identical complex organisms on independent lines of development. For it's quite conceivable that the same effort to turn the same circumstances to good account might have the same result, especially if the problem put by the circumstances is such as to admit of only one solution. The question remains whether the term effort must not then be taken in a deeper sense, a sense even more psychological than any neo-Lamarckian supposes. For a mere variation of size is one thing, and a change of form is another. That an organ can be strengthened and grow by exercise, nobody will deny, but it is a long way from that to the progressive development of an eye like that of the mollusks and of the vertebrae. If this development be ascribed to the influence of light, long continued but passively received, we fall back on the theory we have just criticized. If, on the other hand, an internal activity is appealed to, then it must be something quite different from what we usually call an effort. For never has an effort ever been known to produce the slightest complication of an organ, and yet an enormous number of complications, all admirably coordinated, have been necessary to pass from the pigment spot of the infusorian to the eye of the vertebrae. But even if we accept this notion of the evolutionary process in the case of animals, how can we apply it to plants? Here, variations of form do not seem to imply, nor always lead to, functional changes. And even if the cause of the variation is of a psychological nature, we can hardly call it an effort unless we give a very unusual extension to the meaning of the word. Truth is, it's necessary to dig beneath the effort itself and look for a deeper cause. This is especially necessary, we believe, if we wish to get at a cause of regular hereditary variations. If we're not going to enter here into the controversies over the transmissibility of acquired characters, still less do we wish to take too definite a side on this question, which is not within our province. But we cannot remain completely indifferent to it. Nowhere is it clear that philosophers cannot today content themselves with vague generalities, but must follow the scientists in experimental detail and discuss the results with them. If Spencer had begun by putting to himself the question of the hereditability of acquired characters, his evolutionism would no doubt have taken an altogether different form. If, as seems probable to us, a habit contracted by the individual were transmitted to his descendants only in the very exceptional cases, all the Spencerian psychology would need remaking, and a large part of Spencer's philosophy would fall to pieces. Let us say, then, how the problem seems to us to present itself, and in what direction an attempt might be made to solve it. After having been affirmed as a dogma, the transmissibility of acquired characters has been no less dogmatically denied for reasons drawn a priori from the supposed nature of germinal cells. It is well known how Weissmann was led by his hypothesis of the continuity of the germplasm to regard the germinal cells, ova and spermatozoa, as almost independent of the somatic cells. Starting from this, it has been claimed, and it is still claimed by many, that the hereditary transmission of an acquired character is inconceivable. But if perchance experiment should show that acquired characters are transmissible, it would prove thereby that the germplasm is not so independent of the somatic envelope as has been contended, and the transmissibility of acquired characters would become ipso facto conceivable, which amounts to saying that conceivability and inconceivability have nothing to do with the case, and that experience alone must settle the matter. But it is just here that the difficulty begins. Acquired characters we're speaking of are generally habits or the effects of habit, and at the root of most habits there is a natural disposition, so that one can always ask whether it is really the habit acquired by the soma of the individual that is transmitted, or whether it is not rather a natural aptitude which existed prior to the habit. This aptitude would have remained inherent in the germplasm which the individual bears within him, as it was in the individual himself, and consequently in the germ whence he sprang. Thus, for instance, there is no proof that the mole has become blind because it has formed the habit of living underground. It is perhaps because its eyes were becoming atrophied that it condemned itself to a life underground. If this is the case, the tendency to lose the power of vision has been transmitted from germ to germ without anything being acquired or lost by the soma of the mole itself. From the fact that the son of a fencing master has become a good fencer much more quickly than his father, we cannot infer that the habit of the parent has been transmitted to the child. For certain natural dispositions in course of growth may have passed from the plasma engendering the father to the plasma engendering the son. They have grown on the way by the effect of the primitive impetus and thus assured to the son a greater suppleness than the father had, without troubling, so to speak, about what the father did. So, of many examples drawn from the progressive domestication of animals, it's hard to say whether it is the acquired habit that is transmitted or only a certain natural tendency. That, indeed, which has caused such and such a particular species or certain of its representatives to be specially chosen for domestication. The truth is, when every doubtful case, every fact open to more than one interpretation has been eliminated, there remains hardly a single unquestionable example of acquired and transmitted peculiarities beyond the famous experiments of Brown-Séquard, repeated and confirmed by other physiologists. 1866. By cutting the spinal cord or the sciatic nerve of guinea pigs, Brown-Séquard brought about an epileptic state which was transmitted to the descendants. Lesions of the same sciatic nerve of the restiform body, etc., provoked various troubles in the guinea pig, which its progeny inherited, sometimes in a quite different form. Exophthalmia, loss of toes, etc. But it is not demonstrated that in these different causes of hereditary transmission, there had been a real influence of the soma of the animal on its germplasm. Weissman at once objected that the operations of Brown and Séquard might have introduced certain special microbes into the body of the guinea pig, which had found their means of nutrition in the nervous tissues and transmitted the malady by penetrating into the sexual elements. This objection has been answered by Brown Séquard himself, but a more plausible one might be raised. Some experiments of Voisin and Perron have shown that fits of epilepsy are followed by the elimination of a toxic body, which, when injected into animals, is capable of producing convulsive symptoms. Perhaps the trophic disorders following the nerve lesions made by Brown-Séquard correspond to the formation of precisely this convulsion-causing poison. If so, the toxin passed from the guinea pig to its spermatozoa or ovum and caused the development of the embryo, a general disturbance which, however, had no visible effects except at one point or another of the organism when developed. In that case, what occurred would have been somewhat the same as the experiments of Charin, Delamare, and Moussu, where guinea pigs in gestation, whose liver or kidney was injured, transmitted the lesion to their progeny simply because the injury to the mother's organ had given rise to specific cytotoxins which acted on the corresponding organ of the fetus. It is true that in these experiments, as in the former observation of the same physiologist, it was the already formed fetus that was influenced by the toxins, but other researches of Charin have resulted in showing that the same effect may be produced by an analogous process on the spermatozoa and the ova. To conclude, then, the inheritance of an acquired peculiarity in the experiments of Brown-Séquard can be explained by the effect of a toxin on the germ. This gives you kind of my side note here, gives you kind of a feeling for where people were 115 years ago as far as figuring out how biology worked and how far we've actually come since then. You also see how philosophy sort of plays a role. And I do want to say this seems kind of thick and historically scientific, but we're going to get through this to the more philosophical underpinnings. So bear with us here. The lesion, however well localized, it seems, is transmitted by the same process as, for instance, the taint of alcoholism. But may it not be the same in the case of every acquired peculiarity that has become hereditary? There is indeed one point on which both those who affirm and those who deny the transmissibility of acquired characters are agreed, namely that certain influences, such as that of alcohol, can affect at the same time both the living being and the germplasm it contains. In such case, there is inheritance of a defect, and the result is as if the soma of the parent had acted on the germplasm, although in reality, soma and plasma have simply both suffered the action of the same cause. I think he's using soma here to mean the actual body, and plasma, the sexual cells of ovum and protozoa or spermatozoa. It's not the most natural hypothesis to suppose that things happen in the second case as in the first, and that is the direct effect of the influence of the soma is a general alteration of the germplasm? If this is the case, it's by exception and in some sort by accident that the modification of the descendant is the same as that of the parent. It is like the heritability of the alcoholic taint. It passes from father to children, but it may take a different form in each child, and in none of them be like what it was in the father. Let the letter C represent the change in the plasm, C being either positive or negative, that is to say, showing either the gain or loss of certain substances. The effect will not be an exact reproduction of the cause, nor will the change in the germplasm provoked by certain modification of a certain part of the soma determine a similar modification of the corresponding part of the new organism in process of formation, unless all other nascent parts of this organism enjoy a kind of immunity as regards C. Same part will then undergo alteration in the new organism, because it happens that the development of this part is alone subject to the new influence. And even then, the part might be altered in an entirely different way from that in which the corresponding part was altered in the generating organism. We should propose then to introduce a distinction between the heritability of deviation and that of character. An individual which acquires a new character thereby deviates from the form it had previously had, which form the germs, or oftener the half germs it contains, would have reproduced in their development. If this modification does not involve the production of substances capable of changing the germplasm, or does not so affect nutrition as to deprive the germplasm of certain of its elements, it will have no effect on the offspring of the individual. This is probably the case as a rule. If, on the contrary, it has some effect, this is likely to be due to a chemical change that is induced in the germplasm. This chemical change might, by exception, bring about the original modification again of the organism which the germ is about to develop. But there are as many and more chances that it will do something else. In this latter case, the generated organism will perhaps deviate from the normal type as much as the generating organism, but it will do so differently. It'll have inherited deviation, but not character. In general, therefore, the habits formed by an individual probably no echo in its offspring. And when they have, the modification in the descendants may have no visible likeness to the original one. Such, at least, is the hypothesis which seems to us most likely. In any case, in default of proof to the contrary, and so long as the decisive experiments called for, then there is the possibility, as we shall have. Oh, I lost a page there. And as the experiments called for by an eminent biologist have not been made, we must keep to the actual results of observation. Now, even if we take the most favorable view of the theory of the transmissibility of acquired characters and assume that the ostensible acquired character is not, in most cases, the more or less tardy development of an innate character, facts show us that hereditary transmission is the exception and not the rule. How then shall we expect it to develop an organ such as the eye? When we think of the enormous number of variations all in the same direction that we must suppose to be accumulated before the passage from the pigment spot of the infusorian to the eye of the mollusk and to the vertebrate is possible, we do not see how heredity, as we observe it, could ever have determined this piling up of differences, even supposing that individual efforts could have produced each of them singly. That is to say that neo-Lamarckism is no more able than any other form of evolutionism to solve the problem. In thus submitting the various present forms of evolutionism to a common test, in showing that they all strike against the same insurmountable difficulty, we have in no wise the intention of rejecting them altogether. On the contrary, each of them, being supported by a considerable number of facts, must be true in its way. Each of them must correspond to a certain aspect of the process of evolution. Perhaps even it is necessary that a theory should restrict itself exclusively to a particular point of view in order to remain scientific, i.e., to give a precise direction to researches into detail. But the reality of which each of these theories takes a partial view must transcend them all. And this reality is the special object of philosophy, which is not constrained to scientific precision because it contemplates no practical application. Let us therefore indicate in a word or two the positive contribution that each of the three present forms of evolutionism seem to us to make toward the solution of the problem, what each of them leaves out, and on what point This threefold effort should, in our opinion, converge in order to obtain a more comprehensive, although thereby of necessity, a less definite idea of the evolutionary process. The neo-Darwinians are probably right, we believe, when they teach that the essential causes of variation are the differences inherent in the germ born by the individual and not the experiences or behavior of the individual in the course of his career. Where we fail to follow these biologists is in regarding the differences inherent in the germ as purely accidental and individual. We cannot help believing that these differences are the development of an impulsion which passes from germ to germ across the individuals, that they are therefore not pure accidents, and that they might as well appear at the same time in the same form in all the representatives of the same species, or at least in a certain number of them. Already, in fact, the theory of mutations is modifying Darwinism profoundly on this point. It asserts that at a given moment, after a long period, the entire species is beset with a tendency to change. The tendency to change, therefore, is not accidental. True, the change itself would be accidental since the mutation works according to DeVries in different directions in the different representatives of the species. But first, we must see if the theory is confirmed by many other vegetable species. DeVries has verified it only in Inothera lamarckiana. And then there is the possibility, as we shall explain further on, that the part played by chance is much greater in the variation of plants than that of animals, because in the vegetable world, function does not depend so strictly on form. Be that as it may, the neo-Darwinians are inclined to admit that the periods of mutation are determinate. The direction of the mutation may therefore be so as well, at least in animals, and to the extent we shall have to indicate. We thus arrive at a hypothesis like Eimer's, according to which the variations of different characters continue from generation to generation in definite directions. This hypothesis seems plausible to us within the limits in which Eimer himself retains it. Of course, the evolution of the organic world cannot be predetermined as a whole. We claim, on the contrary, that the spontaneity of life is manifested by a continual creation of new forms succeeding others. But this indeterminism cannot be complete. It must leave a certain part to determination. An organ like the eye, for example, must have been formed by just a continual changing in a definite direction. Indeed, we do not see how otherwise to explain the likeness of structure of the eye in species that have not the same history. Where we differ from Eimer is in his claim that combinations of physical and chemical causes are enough to secure the result. We've tried to prove on the contrary by the example of the eye that if there is orthogenesis, here a psychological cause intervenes. And he means psychological in a 115-year-old way, just a footnote. Certain neo-Lamarckians do indeed resort to a cause of a psychological nature. There, to our thinking, it is one of the most solid positions of neo-Lamarckism. But if this cause is nothing but the conscious effort of the individual, it cannot operate in more than a restricted number of cases, at most in the animal world and not at all in the vegetable kingdom. Even in animals, it'll act only on points which are under the direct or indirect control of the will. And even where it does act, it's not clear how it could compass a change so profound as an increase of complexity. At most, this would be conceivable if the acquired characters were regularly transmitted so as to be added together. But this transmission seems to be the exception rather than the rule. A hereditary change in a definite direction which continues to accumulate and adds to itself so as to build up a more and more complex machine must certainly be related to some sort of effort, but to an effort of far greater depth than the individual effort, far more independent of circumstances, an effort common to most representatives of the same species, inherent in the germs they bear rather than in their substances alone, an effort thereby assured of being passed on to their descendants. So we come back by a somewhat roundabout way to the idea we started from, that of an original impetus of life passing from one generation of germs to the following generation of germs through the development organisms which bridge the individual or the interval between the generations. This impetus, sustained right along the lines of evolution among which it gets divided, is the fundamental cause of variations, at least of those that are regularly passed on, that accumulate and create new species. In general, when species have begun to diverge from a common stock, they accentuate their divergence as they progress in their evolution. Yet, in certain definite points, they may evolve identically. In fact, they must do so if the hypothesis of a common impetus be accepted. This is just what we shall have to show now in a more precise way by the same example we've chosen, the formation of the eye in mollusks and vertebrae. The idea of an original impetus, moreover, will be made clearer. So that's where I guess we'll leave it for today, because we're getting into the beginning. He's just sort of introduced this idea, which he calls the original impetus of life, and that he will turn into his idea of élan vital and vitalism. So we're finishing at the top of page 88, and we will see you next week. Enjoy.